Yeah, so I think my video is on. Audio is okay. Yeah, so uh, 1 second. Yeah, so we'll start. So first, something about condensation. So mostly we'll consider like some problems on this, but there are certain theoretical aspects also which you should be aware of. So we'll start with those, and maybe in the second half of the class, some basic problems of radiation. So radiation will be in the next week. It will be discussed, in details. This time we will only go for what you say, the introductory, some definitions, some concepts like that, and yeah, major part of radiation will be taken up in the next class. That will be a dedicated class for radiation itself, and I think uh, yeah, after that maybe one more class will be
बोले
there. Uh, someone's audio is not mute. Can you please mute yourself? So yeah, we'll start. So boiling we already covered in the last class. So now this second half of it, which is called as, I mean, it is a condensation process, but typically boiling and condensation are studied together. Here we are studying them differently in a different case. So yeah, so as it was told in the class, there are like four major types of condensation processes. So first is dropwise, then there is dropwise suspended. So first dropwise is nothing but on a surface, and second is suspended. So it will be having certain nucleation sites in the suspended state, and there the condensation starts. Then there is, or maybe I should write, uh, since these are types, we can number them. Then there is like famous film-wise condensation, and it is also studied like we have done in the class also. Sir has done some governing equations, simplifications, etc. And fourth is direct. So these four types you should be aware of. Uh, yeah. So apart from that, yeah, going back to the curve. See, doing analytical solution for dropwise condensation is not easy because there is no such pattern for it. But you can do some experiments and get some correlations. That is possible. And mostly dropwise condensation is studied like that only. Mostly it is experimental based and then derivation of some correlations like that. Film wise condensation, it is studied. It can be studied analytically under certain assumptions, and those assumptions and all that derivation itself is covered in the class by professor. So you know what it is. Uh, then this other last category, which is direct condensation, it's not that widely studied because in many applications, typically there is a surface involved and condensation happens on the surface. For example, like in heat exchanger, etc. Direct condensation is okay, maybe in some applications, but not that widely studied. So that is also again, if somebody is curious about that, it will be mostly experimental basis. So film-wise condensation has some formula, and you know, uh, it is like if when it is in the laminar region, it is called as a Nusselt film condensation analysis also, and the same thing was done in the class. So we'll not go into the detail, but I'll just write down some important observations from there. So this was your y-axis here, and this was your x-axis, and u infinity is 0 here. It's a stationary environment there, and this is the direction of your maybe I should show like this. Your gravity vector is like this, and the velocity profile, it is 0 at the interface and 0 at the free surface as well. So this it should be something like this. This is your velocity profile, or u profile here. I'll write u is your x direction velocity, and temperature profile will look nothing like, I mean, something like this, because since it's a condensation, your surface will be colder than the ambient. You know, your T infinity will be typically greater than your T surface. Therefore, this will be your temperature profile as a function of y. So there were certain assumptions. U and V are very small, therefore we neglect the convective effects. And then you simplify the continuity and x momentum equation. Then you use that boundary layer assumption, and sorry, not boundary layer. You assume that outside the boundary layer, the pressure gradient is, you know, essentially equal to the hydrostatic gradient, and then you know, replace that term in the x momentum equation within the boundary layer. And when you do all this, you get this velocity profile as uh, rho v minus rho l into g into delta square divided by mu, and you have this y by delta minus 1 by 2 y by delta whole square. But here the unknown was delta, which is boundary layer thickness. That is a function of x. So to do that, basically the whole condensation rate, etc., were calculated, and in the end, when you equate those two, what you get is boundary layer thickness as 4k liquid into liquid viscosity into delta T. Delta T is your difference between saturation temperature and your surface temperature. Yeah. And in the denominator you have G, rho L, and density difference. So that will be rho L minus rho V. Rho V is your vapor density, which will be surrounding your boundary layer. So all those things are already discussed. I'm just noting down the formula here so that you'll have some idea what we are talking about. And then, since we neglect the we neglect your convective effects, so this essentially becomes your uh, flux balance, and therefore you get H as liquid density, thermal conductivity divided by X. And here we know, since your delta of X is proportional to the, or maybe I should use this, is proportional to x power 1 by 4. Therefore your H of X will be proportional to your x power minus 1 by 4. So what it means, as your X increases, that means as the distance from the top along the length in the downward direction increases, your heat transfer coefficient decreases. And it is typically true also for other boundary layers that we saw earlier also. And then you can find your average heat transfer coefficient at any location by doing this integration. That you know this, right? We have done this a lot of times by now. And when you do that, you get your h bar at any location x uh, as 4 by 3 into h of x. You can take x as L also. It doesn't matter. The main thing is this number. So 4 by 3 is equal to some 1.33 also. In some competitive exams like GATE and all, they'll directly ask you this. In case of condensation, what is the ratio of average heat transfer coefficient to the local heat transfer coefficient during the film-wise condensation? Or sometimes they directly call it as Nusselt condensation. So that is there. And then there is a famous uh, correlation, which I think you can use it in some problems in your assignments also. So it will be your heat transfer coefficient, average heat transfer coefficient into length of the plate divided by thermal conductivity of the liquid into this constant. You may wonder where these constants come from, but these are like experimentally, like you get the form of equation doing analysis, but the exact constant, etc., typically they are derived or deduced from your experimental data. So here you'll have G rho L density of your differential density. You have HFG dash here. So what it means is, during the condensation process, you can assume the HFG at T sat or saturation temperature correspondingly. You can assume HFG, but there will be some correction, and that is what HFG dash represents. There will be some correlation given so that you can, use that correlation to get HFG dash, and that will be D will be your. Oh, I'm sorry. That expression is for cylinder. This one, since we are on the flat plate only, here you'll have KL. Okay, so this is there, and let me see if we have some problems here. Yeah. So then there are correlations for cylinders, cascade of cylinders, and laminar turbulent flow. There is a correlation for turbulent flow also, which was given in the class. Typically, when you in this assignment, there will be a point where you will not have correlations directly available to you, but nonetheless, when you appear for any exam or anything, there the correlations will be given to you. You are not expected to mug up all these things. So yeah, like that. Let me just see if we can find some problem. So in your assignment, all problems are basically tube, 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 array of tubes. And there is this different problem. 1 second. Okay, 1 second. Hx power 1 by 4, huh? I think it's 1 by 4 in the power. 1 by 4 of Nusselt number you are saying? 1 second. Mu L. Uh, 1 second. Is it 1 by 4 or 1 by... Yeah, it's okay. Yeah, I think it is 1 by 4 here. One can cross check that, but maybe I did some, while noting it down, I did some mistake, but you get the point, right? So anyway, there are like certain types of questions which can be asked from this category. For example, one question could be, let's say, for a film wise laminar condensation over a vertical flat plate, h at x equal to 1 meter from top is, let's say, 100 watt per meter square Kelvin. Then what will be the h value at x equal to 3 meters. So basically this is like, I have made this up on the spot, this question, but the point that I'm driving home here is you have to use this expression here. You know that for a laminar film wise condensation, your local heat transfer coefficient is proportional to the minus 1/4 power of your distance from the top, or the vertical distance from the top here. So that is one type of problems that is typically asked. So we know that this is your solution. We know that local heat transfer coefficient is proportional to minus 1/4. Therefore, h2 by h1 will be x1 by x2 raised to 1/4, right? And here, x1 is 1 meter and h1 is 100, x2 is 3 meters and h2 is unknown. So therefore, h2 will be h1 into this x1 by x2, 1/4. This is 100 into x1 is 1, x2 is 3, and whole thing raised to 1/4, right? So we'll do this calculation. So 1 divided by 3. And the whole thing is raised to 1 divided by 4. So you have into 100. Yeah, so therefore you get your heat transfer coefficient at x equal to 3 meters as 75.984. So this is a one sample problem that can be asked from here, and typically this is a good candidate for gate question, data entry, or maybe something like that. Apart from that, another case could be similarly, they'll give you yeah, I mean, the next part or the case 2 could be what is the Nusselt number at x equal to 3 meters. What is the Nusselt number at x equal to 3 meters divided by Nusselt number at x equal to 1 meter. So this could be another problem which can be framed from this, like a simple 1 mark question. So here you can, you know that your Nusselt number at any location x is nothing but it's proportional to the local heat transfer coefficient, and your x coordinate itself. So therefore Nusselt number is x equal to 3 meters and divided by Nusselt number at x equal to 1 meter, it will be equal to your first heat transfer coefficient h1, sorry, this 2 and x2 divided by h1 x1, right? So h2 is 75.984 into x2 is 3 divided by 100 was your h1 and x1 is 1. So I mean you get the point, right, what I'm trying to say here. So this will be nothing but equal to 227.951 divided by 100. It is nothing but 2.279. So this is your answer. So these types of questions can be framed, okay, is what I'm trying to say here. Other than that, yeah, then there will be another set of questions which will be like subjective questions, and for that you need a lot of data, etc., etc. But before going there, let me see if there are certain questions from this condensation topic where you can simply use the correlations or something like that. Yeah, 1 second. Yeah, so there was one question. Yeah, okay. This was like 2016 ESE question. So the question is, a circular pipe of diameter 10 centimeter and length 10 meter is used for steam condensation on its outer surface. So this is typically a case of tube in a heat exchanger. There are like in typical heat exchanger there will be multiple passes and all. Here they have not given that information because it is not required for problem solving. And then what they have asked is the average heat transfer coefficient, they have denoted by H under subscript H, when pipe is horizontal is n times the average heat transfer coefficient when pipe is vertical then what is the value of n is the question. And here you need certain correlations to be like you can't like it's not expected of you to remember the correlations. Here it is given that this heat transfer coefficient for horizontal pipe or horizontal tube case is given as 0.725 into rho L minus rho V KL cube G into HFG divided by mu into Tsat minus Ts into D, whole thing raised to 1 by 4. And your heat transfer coefficient for vertical case is given as 0.943 into again the same thing, except the fact that here it is, instead of D it will be L. So basically the whole thing inside the bracket is same, the other terms are same, instead of D only L is there, and the outside constant is changed. So this is what is given in the question. So now one can simply do this, because so now what they have mentioned is your heat transfer coefficient in horizontal case or horizontal tube is n times of the heat transfer coefficient in vertical tube or pipe. So therefore, you can put these expressions and cancel out the terms. So what I can do is I'll just replace these terms with some C divided by D power 1 by 4 will be n into 0.943, and the C is same in this case also, right? Because the fluid properties and delta T etc. remain same, and there will be L power 1 by 4 here, right? So this C will get cancelled, and since you are interested in finding out N, what you can do is it will be 0.725 divided by 0.943 and L by D power 1 by 4. So L by D is nothing but L is your length, which is 10 meters, and D is your diameter, that is 0.1 meter. So 10 by 0.1, that will be 100. So therefore your N will be 0.725 to 943 into 10 by 0.1 raised to 1 by 4. So if you simplify this, what do you get? 100 raised to 1 divided by 4. So this term is 3.162. 3.162 into 0.725 divided by 943. And you get 2.431. So these type of questions are also asked. And one thing you can note here is, okay, we solved the problem, but what it essentially says is when you keep the tube horizontal, you get the heat transfer coefficient at like 2.4 times as compared to vertical tube, and therefore in practical applications also mostly the heat transfer tubes are horizontal. I mean, wherever the condensation is supposed to take place. So if somebody is interested in why the tubes are always horizontal and not vertical, maybe you can think of it in this way. Okay, so these type of questions are there, which need your understanding of your correlations, etc. And yeah, then there is typical questions which we will consider, but yeah. Okay, so we'll take one subjective problem. See, the thing is, I mean, I don't want to repeat here because this type of problems are typically discussed by other TAs also, but we don't have choice here because uh, I say? I mean, these are like certain like templates, and you have to do those. I mean, I understand if you think this is repeated and all, but uh, yeah, you have to bear with me. Before that, uh, one second. Mm, 25, 24. Okay. Yeah, we can take one flat plate problem and one cylindrical problem maybe, so that we'll be done with this. So yeah. Hmm. Reynolds number is in this case okay. So I mean, there is a vertical plate, something like this, and I think this is your assignment problem also. But let me see if I can modify this in some way. Hmm. Okay, so yeah, we'll go ahead with this, but what I should say is, hmm, one second. 4a by p, right? So okay, so this is your first case where your length of the flat surface is 500 mm, width is 200 mm, and the P atmosphere is 180 m. So basically, it is a atmospheric ambient. And the question is, at what surface temperature, which is Ts. So this Ts plate must be maintained to achieve condensation rate of 25 kg per hour. So I think this is your assignment problem also. So let me just see. Oh no. So okay. But yeah, I think this was taken by some other person also. But what I mean to say here is, this is a general template, okay? So okay, so the solution is, or before going to the solution, what all things are given to you, that should also be first mentioned. So for water, when it is in vapor state, or for water vapor also you can see. Tsat at 1 atm, Tsat will be 100 degrees Celsius. Typically we take 100, but in reality it is not 100. That also you should remember. In Bangalore it is 97 or 98, something like that. Yeah, I mean it depends on your sea level height, etc., etc. All those things. But typically we assume 100. And for liquid water, so this type of information will be given to you in the problem itself. No need to mug up or anything. And again, these properties will be at T average. So they have mentioned like you know, I mean, you need not to worry because typically these things are at average film temperature only. Here we don't know the TS, so we can't be sure. But they have given something in the problem. But let's not go there. 967.1 kg per meter cube. Cp liquid of water is 4.2 typically. So that will be joule per kg Kelvin. Dynamic viscosity is 324 into 10 to the power minus 6 Newton second per meter square. Thermal conductivity 0.674 watt per meter square Kelvin. Oh, sorry, watt per meter Kelvin. And your kinematic viscosity is given as 3.35 into 10 to the power minus 7 meters square per second. And some correlations are also given. Your mass flow rate is nothing but your flux divided by HFG, and this is corrected HFG. This will be nothing. Yeah, this is not flux, this is the total heat. Your average heat transfer coefficient along the length into area of the length into Tsat minus Ts divided by HFG dash, and HFG dash is nothing but HFG into 1 plus 0.68 into Jacob number. So this Jacob number is, I think it was discussed in the class also, it is basically ratio of sensible heat divided by latent heat. So it is a measure of that quantity. So therefore you have Cp delta T at the numerator and HFG at the denominator. So now question here is this Ts is unknown, right? Because this delta T is unknown. So Tsat, you know, 100 degrees, but this is Ts is unknown. So this 1 second. Here it will be Ts, not TL. So your Ts is unknown, so you can't find Jacob number, you can't find this, and when you can't find this, the whole thing is basically is function of Ts here. So you need to start from Reynolds number, as is the case always. So let's say this is your first case, and Reynolds number formula here is 4m dot by liquid dynamic viscosity into thickness or the width of the plate. This was discussed in the class also, this correlation, how it comes. So in this problem it is 4 into m dot is 25 kg per hour, right? So you need to convert it into kg per second because everything is in SI units, divided by mu L is given as 324 into 10 to the power minus 6 into your thickness is 0.2, 200 mm. And when you calculate this, you get 428.66. This is your Reynolds number. And typically, when it is greater than 30, we call it as turbulent. There is no hard rule like that, but typically less than 30 is your laminar, and greater than 30 typically till 1800 you assume it as a transition and then turbulent. So let's not go there because that is also dicey. So now based on your Reynolds number, there are like correlations for uh, Nusselt number, average Nusselt number along the plate. Okay, so this they typically given it as h bar L into your kinematic viscosity power square by G into power 1 by 3 divided by K of L. So one thing you can note here is your kinematic viscosity is having units of meter square per second, right? Yeah, and your G has units of G is acceleration due to gravity, that will be meter per second square, right? So I can write it this as meter s power minus 1 and this will be s minus 2. So when you take VL by VL square by G, what are the units? There will be m power 4 s minus 2 divided by ms minus 2. So your second will get cancelled and what you are left with is meter cube, and then you take the cube root here, right? So basically this is some length scale. What I'm trying to say here is typically you have HL into L by K, right? But here they have replaced it by this length scale. Why? Because there will be reason to it, but we can't go into those details right now. It will take a lot of time to discuss all those things, and we don't know the derivation also. So like that. First case is it is 1.4 into Reynolds power minus 1 by 3. If your Reynolds number is less than 30, it is Reynolds number by 1.08 Reynolds number power 1.22 minus 5.2 when your Reynolds number is between 30 to 1800, and this thing will be Reynolds number divided by 8750 plus 58 Reynolds number minus 0.5 into Reynolds number 0.75 minus 253. So some complex looking and this is valid when your Reynolds number is greater than 1800. So exact limits, don't worry. Typically, like that is it is there. It was 7. So yeah, this is actually from a textbook. So don't worry. The point I'm trying to make here is you should understand. Sometimes they change the length scale like this, and sometimes your Nusselt number correlations are typically function of your Reynolds number. So you need to first calculate the Reynolds number and check which Nusselt number you need to use. So here we have 428.66. So we need to use the second correlation for getting the Nusselt number. And yeah, so then what happens? Since your Reynolds number is in the range of 30 to 1800, you need to use the second correlation, and second correlation will give you the average heat transfer coefficient as, I'm just taking this length scale and K on the other side and directly writing the coefficients correlation, sorry, 1.08 into RE power 1.22 minus 5.2. So everything you know, yeah, right. So Reynolds number is known, KL and this. Okay, we'll calculate this ratio. So what is your KL? Yeah. Before that, yeah. Okay. So what is your KL? It is given as 0.674. And your kinematic viscosity is given as I think 10 to the power 7, 3.35 into 10 to the power minus 7 whole square divided by 9.81, and whole thing is raised to 1 by 3. Your Reynolds number is 428.66, so you can put it directly here. 1.08 428.66 power 1.22 minus 5.2. So first ratio we can calculate because we'll use it in some other problems also. So what is it? Okay, it is a ratio. So numerator you have 0.674. Denominator is a big number. So what we'll do is the whole thing is raised to 1 by 3, right? So here we'll put a bracket. Okay. So this is a square. 3.35. Where is there? 10 to the power wala. 1 second. Where is that 10 to the power wala button? 3.35 into 10 to the power. Okay, into 10 to the power minus 7 divided by 9.81. Yeah, so this ratio becomes 29912.522. And now the other thing. Okay, 428.66 divided by 1.08 into 1.22 power 42.66 minus 5.2. Yeah, so this is 0.245 into 299.12.522. Yeah, so this whole thing gives you your average heat transfer coefficient as 7322.378 watt per meter square Kelvin. And now you can use this m dot correlation, right? Because you know this one. Because in this correlation, the only unknown here is Ts, and in the denominator also it comes because of this correlation, which is also a function of Ts. So therefore, you can write your m dot as h bar L into A into Tsat minus Ts. Now HFG dash, which is corrected HFG, is nothing but HFG into 1 plus 0.68 into Jacob number, right? And what is Jacob number? CPL Ts minus Tsat. CPL into Tsat minus Ts, sorry, divided by HFG. So if you simplify, what will happen? You can take HFG common and cut it. So what I mean by that is this will go away, this HFG term will remain here, and then you have to take inverse. So therefore your 1 by m dot will be your HFG plus 0.68 CPL Tsat minus Ts divided by h bar L into A into Tsat minus Ts, right? So now we can solve it, right? So yeah, so basically you'll have one term which will be h bar L into A minus m dot into 0.68 into Cp of L into Tsat minus Ts will be equal to HFG. Am I right here or did I do some mistake? Yeah, m dot will be here. Yeah. So your Tsat minus Ts will be m dot HFG by HLA, and 1 second, no? This whole thing will be there, right? So this will be again m dot into 0.68 Cp of liquid. So now you can solve, right? Because you know m dot, you know HFG, and you know everything is known here. Area is nothing but 500 into 200 mm square. That's the surface area of condensation. So we'll do that, and that will be your m dot is 25 by 36,000. So 25 by, this is your kg per second. HFG is nothing but what is the HFG value? 2257 into 10 to the power 3. H bar L we calculated 7,000. See, you can see one thing also. See, H bar value, since it's condensation, it is 7,000. Typically, that is what you observe in condensation and boiling. The heat transfer coefficient should be around 10,000, and it is close to that. So your calculations are correct. So that can be your one check also. 22.378 into area is 0.5 into 0.2. So this is one term. Minus 0.68 into Cp liquid is 4203 into your mass flow rate is 25 by 3600. Yeah, so this looks somewhat tedious, but one can solve it. And when you do that, I'm not doing it because it will take a lot of time. I want to tell you something else also. So there you'll get Tsat minus Ts as 22.01. So like that you'll get, and therefore your Ts will be 100 minus 22.01 degrees. Here no need. Therefore your Ts will be 77.99 degrees Celsius. So see, calculating Ts is not the main objective. So this was the solved problem. What I wanted to tell you is I can modify this problem and whole thing also changes. So what I can do is case 2 will be I'll make the width of the plate is reduced to 100 mm. So earlier it was 200 mm. Now I have reduced it to the 100 mm, and the m dot of, or the condensation rate required is, let's say, 5 kg per hour. So I have reduced that also. So in that case, what happens? Your Reynolds number, which is 4 m dot by mu L into B, it's a 4 into 5 by 36. So this is your kg per second. Mu L is given as 324 into 10 to the power minus 6, and your width is now 0.1 instead of 0.2. So this is a second case of the problem, and if you do that, what you get is, basically you have 4 into 520 in the numerator, and denominator will be 3600 into 0.1 into 324 into 10 to the power minus 6. So you'll have, one second. Oh. Here also you get 173. I wanted to bring it to, you know, one second. I'll do this way. This is 3 to 4. Yeah. So instead of 5, I want 0.5 only. I don't want very high condensation rate in this case. So if you do that, you get Reynolds number of 17.147. So which is less than 30. So now, therefore, you have to use the Nusselt number equation or correlation, which is given by this formula, right? So then what happens? Therefore, your average Nusselt number correlation becomes 1. What is it? 1.43 into R e power minus 1 by 3. 1.43 into R e power minus 1 by 3. So what I'm trying to say here is, you know, if you do this, minus 1 divided by 3 and into 1.43, so you'll get Nusselt number of 0.555, and then again you need to, this will be h bar L into this square by G power 1 by 3 divided by KL, and if you do that, you'll get h bar L as this ratio we had calculated right earlier only. Yeah. So into 29912.522. Yeah. So you get heat transfer coefficient of the order 16,588.033 or 34. You can take it as, this will be your watt per meter square Kelvin. So now you see your Nusselt number is decreased, but your what you say, your average heat transfer coefficient is almost doubled. So, and then you can repeat the same procedure to get the TS. So that is one type of problem. Another problem is, instead of keeping TS as unknown, uh, TS is known and m dot is unknown. So this is another category of problem where I'll give you TS, the surface temperature of the plate at which the condensation is happening, and I will ask you to find out what is the condensation rate that we can expect in this problem. So in this case, what happens? Your m dot is unknown, right? So you cannot directly use any correlation. So there, the correlation will also have to be provided to you, because see, if m dot is unknown, you cannot calculate the Reynolds number, right? And if you cannot calculate the Reynolds number, you'll not know which Nusselt number correlation to be used out of these three. So in that case, if TS is known and m dot is unknown, what the question setter will do is he or she will give you the correlation also along with the question, and in that case, now your Reynolds number is function of m dot, so Nusselt number is function of m dot, so your h bar, so this is also function of m dot, right? So then when you put it in the final equation like this, your equation will be having unknown, that is m dot, and you solve for m dot. In this case, your equation had unknown TS, so you solve for TS. So that's how the third variation of this problem will go. Okay. I hope I made sense. Okay. Yeah. So like these are the typical types of problems that will be asked, from this category. And now what happens, instead of flat plate, you'll have a tube or cascade of tubes. In those problems also, there is no major change, only the Nusselt number correlation changes. And depending on that, again, you'll have these three cases. First case will be for the tube, they'll not mention what is the surface temperature of tube at which the condensation is happening. They'll directly give you the condensation rate. Second is, they'll not give you condensation rate and give the temperature of the surface. So that is the second variation. And then you'll have sub variations of these problems. So I hope you get my point, and you need to solve those questions like that. So that is there. So like, I hope everything is clear. If not, you can ask any doubt if you have. But what I'm trying to do here is, because if you solve every category problem, it will take a lot of time. I'm just trying to give you the one second. Sorry. Uh, yeah. So. Hmm. Yeah, 7319. Okay, because it's a calculation of thousands of order. There will be some error. That is okay. But I hope what I'm trying to convey here is clear, that there will be majorly. Okay, I'll write it here. Uh, note as a note. So first problem will be m dot is known. So your condensation rate is known, and you solve for TS, which is unknown. This is easy case because from m dot you can calculate Reynolds number, and from Reynolds number you get the Nusselt number correlation using correlation, and then you get h bar L, and the life is easier because then you put this into that m dot formula, which is h bar L into A into T sat minus TS divided by HFG dash, or corrected HFG. But second case, which is slightly tricky, is TS is known and you solve for m dot is unknown. In that case, what happens? You don't know Reynolds number, right? So therefore, Nusselt number correlation is also given. And then again, you calculate h dash, h bar L, and h bar L will be, this h bar L will be some function of m dot. And then again, you plug it back in your m dot correlation, and then you solve for m dot like that. So it's all like that only. So now, with that, we'll stop the condensation case. Let me just check whether I have missed anything about condensation. Then we'll move ahead with the radiation, introduction to radiation. I think we'll have a dedicated class for radiation next time. So right now we'll take some simple problems only. And yeah, let me just see what am I missing here.
Hello, excuse me, sir. 1 minute.
Yeah, tell me.
Sir, you said one more case is there, sir. What is the third case?
Previously, yeah, this one.
On this cylinders. In cylinders, third case, how it will come?
No. Like there are major two cases, whether it's a flat plate or cylinder. Third case will be which I showed here in the case of flat plate. Here, what I did because there are three Nusselt number correlations, right? Yeah,
Yes, sir.
this. So what I did initially, like in the given data from the given data of the questions, our Reynolds number came into the second category. But then what I did, I changed the data so that Reynolds number comes into the first category. And then your Nusselt number correlation changes, and again you have to repeat the process, right? So same thing I can do for cylinders also, because for cylinders also there will be correlation for laminar and turbulent regime, and I can give you a set of parameters such that in first case it will be a laminar condensation flow, in second case it will be a turbulent condensation or condensation in the turbulent regime, something like that. So those are some variations. So maybe I can mention it here only. uh, yeah, so this Nusselt number correlation, right? So this can be laminar or turbulent. So that will be another variation of the problem. And in the second case, where your TS is known and M dot is unknown, this Nusselt number correlation is given to you, and therefore I cannot change the problem there. So this is possible in the first case, but in the second case, since I have to specify the Nusselt number correlation, uh, I cannot play with this variable here. So like that problem can be framed. Okay, I hope it is clear. Yeah, so basically two main cases, and then you can have different sub variations of those cases depending on your Nusselt number regime, etc. So apart from that, mm, yeah, see, one thing is there which I would like to mention here before we close this radiation thing. Typically, we study film condensation, etc., because that is easy to study analytically. But in reality, film condensation is not good, because what happens when the film is formed, the condensate covers the surface area of your tube or flat plate or whatever it is, and the next set of vapor doesn't have a proper area for condensation. So in practical case, uh, what we do is we hope that even though the film is formed, the condensate will quickly flow away or drop down. That's why typically the uh, if it is a flat plate, it will be vertical. If it is a tube, it will be designed in such a way that the condensate falls down. So that's why typically even like we study film condensation, but in reality, film condensation which doesn't fall down is not good. So that is one thing, but I don't think it is relevant here. Yeah, so I think we are done with the uh, radiation. So now let's move to the uh, sorry, we are done with the condensation. Let's go to the radiation part. So next class we'll discuss important terms in the radiation. For now, this class will just have this introductory idea about black body, etc., etc., and some basic questions we'll take. So like that. 1 second. '53. Yeah, so this is like a 1 second. Yeah, so let's start with radiation. So like different definitions are already discussed in the class. So I'll try to focus on some basic sort of problems from condensation, and we'll see if something else is remaining. We can cover it in next class also, because we'll have a dedicated class for that. Yeah, so okay. Yeah, so let's take some simple questions. These are like uh, first level difficulty in the radiation topic. So there is a solid sphere of diameter 10 centimeter. So it's a solid sphere of diameter 10 centimeter, and it is at 100 degrees Celsius temperature. It is in a room, it is suspended in a room by a string or whatever is the mechanism, and your room temperature is 30 degrees Celsius. And first you need to find rate of heat transfer by radiation, and second you need to find time taken by sphere to cool down to 500 degrees Celsius, assuming it has a black body. And they have given you the density of the sphere as 8680 kg per meter cube, and specific it, or it should not be CP, just C. It is at 98. 1 second, I think there is printing mistake here. 1 second. CP of steel is around 500, right? Yeah, so let's take 500 because it looks like a steel ball. So joule per kg Kelvin. Okay, so this is a typical problem. So here you need to start with the first law, or energy balance. So from energy balance of solid sphere, what you have, that whatever heat it is losing due to its temperature change or because of the radiation, and that is happening because the room is colder as compared to wall. So that rate of change is nothing but the energy gained by radiation due to energy gained by room due to radiation heat transfer, and that is typically sigma A T power 4 minus T power T infinity power 4. So this part is clear, right? This is your uh, uh, heat gain, heat gain by the room due to uh, or sorry, this should be 1 second. the rate of temperature is decreasing. So yeah, so it's clear, right? Whatever heat the ball is losing, this is the heat that ball is losing, and this is the heat like heat transfer taking from ball to the infinity or the what you call your room, which is at T infinity. Negative sign is here because the ball is losing the heat and the heat is transferring to the room. So now, what is the mass of the ball? It will be density of the ball into volume. So since it's a sphere, it will be 4 pi 3 pi r cube. So density is given at 8680. 4 by 3 pi. The radius is 5 centimeter, right? So it will be 0.05 cube. Okay. Cp is around 500 given joule per kg Kelvin. This sigma is a constant, and that is 5.67 into 10 to the power minus 8. I think it is called as a Stefan Boltzmann constant. I forgot what it is called. No, it's Planck's constant, I think. No? Sorry, it's not Planck. Planck's is H. So this is sigma. This is, yeah, it's Stefan Boltzmann. I was correct initially. It will be meter square Kelvin power 4. So you need to pay attention to the units also. This is also important. Sometimes people forget those. And area will be 4 pi r square because it's a sphere. So the outer surface area is 4 pi r square. So 4 pi 0.05 square. And before solving, what we can do, we can simplify. So from equation 1, we can simplify it as dt by t power 4 minus t infinity power 4. This will be your temperature terms, and then you will have some dt into constants. So what all constants will be there? Sigma a will be as it is, and this minus sign, let's say we take this side, and you'll have mcp. So you can simplify here so that we need not calculate everything. 4 pi r square density into 4 by 3 pi r cube into cp dt, right? So this 4 goes away, pi goes away, only r remains in the denominator, and you'll have minus sigma dt into 3 will be there to go into our cp. So this will be your simplified governing equation for this flow. So now first we'll see what is asked in the question. Oh, okay, so the first part is rate of heat transfer by radiation. So rate of heat transfer by radiation will be nothing but sigma t power 4 minus t infinity power 4, right? Into area, of course. Yeah, so there will be area, and yeah, if you do this calculation, one more thing, you need to put this temperature in Kelvin, not degree Celsius. So that is an important point here. So your T will be 1000 plus 273, 1273 Kelvin, and your T infinity, which is room, that will be 30 plus 273, so that will be 303 Kelvin. So That is very important thing. If you put them in degrees and instead of Kelvin, you'll get definitely wrong answers. So if you do that, area is 4 pi r square. What you should get is approximately 4.662 kilowatt. So I leave the calculations to you because I think you can do that. The main part, the second part. So we need to calculate the time, so that like we need to calculate time in which the temperature of ball decreases from 1000 to 500 degrees Celsius. So from equation 2 you can write, you have to integrate the equation. So dt by t power 4 minus this t infinity is constant, but for the sake of this thing I'm writing it as it is. And you can do one thing actually, you can take this minus sign on this side. So what happens when you take the limits? So your T will be 1273 Kelvin here, T1, and T2 will be 500. So 500 plus 273, it is 773 Kelvin. So you can reverse the limit because you have negative side already, negative sign. So this will become T2 which is 773 and T1 which is 1273 Kelvin, and the integral remains same, T power 4 minus T infinity power 4. Now the question is, how do you integrate this guy? And on the other side, you'll have from t equal to 0 to that time that is unknown. I should not use capital T because that's temperature. Let's say we'll put it as T only. And you'll have 3 sigma dt by rho r Cp. So this is all constants. You'll essentially get 3 sigma E by rho r Cp, right? So there is no need to do any integrand on this side. But the question is, what about this guy? So you have 4th power integral, right, at the denominator. So how do you do that? And that is the tricky part here, which I wanted to discuss. So, 1 second. One divided by, you have x power 4 minus some constant which is also power 4. And the integration with respect to that x. So the trick is you have to uh, 1 second. Arre baapre. This has given some random answer. Basically, you have to do it by parts. And how you do it is like this. So for simplification, I'll write something like this. So this is like integration of this sort, right? Into dx is already there. So what you do, you basically use a square minus b square formula. You end up it right like this, right? And then you separate the two fractions. So for that, what you do, what can be done? So you can write it as some a x square plus a square plus b x square minus a square, and the whole thing is again with the integration. So when you solve this, what you get is basically a plus b equal to 0, and a into a square plus b into a square equal to 1. So your a is equal to minus b basically. So you can put them as b will be that will be 2b square, so 1 by 2 a square, and a will be minus 1 by 2 a square. I hope this math is clear. Yeah, so therefore what you get is a is your minus 1 by 2 a square, right? So you can take it out of the bracket, 2a square dx by x square plus a square, and then b is 1 by 2 a square into dx by x square minus a square. So now 1 by x square plus a square, I think that is tan inverse 1 by tan inverse x by a, right? One second. 1 by x square plus a square. Yeah, I think it is tan inverse only. Let me just. Yeah. Okay, it's tan inverse x by a by a. So this is minus 1 by 2 a cube into tan inverse x by a. First term is this. And what about x square minus a square? There again you can do the calculations because it's not that tough. Again, you can do some substitutions, or you can again take it as x minus a plus x minus a into x minus b, or it's directly tan h inverse. Okay. Yeah, so what you can do here is you can again split it into some constant a dash by x minus or x plus a plus b dash into x minus a into dx, and then what you get is same, a dash plus b dash equal to 0 because there is no x term in the numerator, and minus a dash into a plus b dash into a will be equal to 1. So I think same thing you get, that you get b dash as 1 by 2a and a dash as minus 1 by 2a. So essentially you have this integration of this form, minus 1 by 2a integration of dx by x plus a plus 1 by 2a integration of dx x minus a. And you know that 1 by x plus a integration is ln x plus a, right? Yeah, so yeah, so you have minus 1 by 2a ln x plus a plus 1 by 2a ln x minus a. Therefore, you have 1 by 2a ln x minus a divided by ln x plus a. So this whole thing, I'm just adding it together. But can we do that? One second. Yeah, I can take 1 by 2 common, then this will be like this. And you have this factor already multiplying outside, right? So finally, after all these calculations, what you get is, first term you have minus 1 by 2a cube into tan inverse x by a, and then you have plus 1 by 4a cube ln x minus a divided by ln x plus a. I hope I have not done any mistake here. Let me just check once. 1 a equal to b. Yeah, I think it's okay. So therefore, in our case, our integral is dt by t power 4 minus t infinity power 4, right? So by this logic, here t infinity is a and t is t. So it will be minus 1 by 2 into t infinity cube into tan inverse t by t infinity plus 1 by 4 t infinity cube into ln t plus t infinity by ln t minus t infinity. Oh, sorry. Minus super plus, like this. And yeah, so basically then we have to put the limits and all. So our limits are 773, 1273. So 773, 1273. What is tan inverse? 773, and t infinity is nothing but 303, that we should remember. Okay, one second. Yeah, I'm just worried whether it is coming minus or something like that. Not really. Okay, so tan inverse, so this will be 1 minus 2, 303 cube into tan inverse, what is t 1723 by 303 minus tan inverse, or maybe I should write it this way, 773 by 303. This will be your first term, plus 1 by 4 303 cube into ln. The first term will be 1273 plus 303 divided by ln 1273 minus 303 minus ln 773, numerator is minus 303 divided by ln 773 plus 303. Yeah, so it looks slightly complicated, but yeah, this is what it is. So let me just calculate these terms. Forgive me if it is too complex, but this is the way to solve these type of problems, and this is a classic subjective problem from this topic. So you have to do this way. opened. Yeah. So let's see. It is tan inverse. Tan inverse 1273 divided by 303. So you have 1 by minus 1 by 2 into 303 cube 76.612 minus 773. This is 68.596. So this is your first term. Then you have 4 into 303 cube. And what is this first term? So you have a ratio of logarithmic terms. So ln 1273 minus 303 divided by ln 773 minus 303. Therefore, the first term is 1.118 minus second term is, oh, I'm sorry. This is 1273 plus 303. Yeah, so this is 0.94934. And then you have 773. This is your 0.881. Okay. Hope I'm not doing any mistake here, because this negative sign is, I'm worried about it, whether it should be there or not. But okay, let's see. So basically you will have 1 by 2303 cube common, and there will be divided by 2, right? So first term is 76.612 minus 68.596 and minus, so this is minus 8.016. The integration looks okay only, but why am I getting minus terms here? That is the question. And there will be plus this 0.943 minus 0.881 divided by 2 will be there. So this will be 0.031. No, this total integration should not be negative, because right hand side you have time. So either I have done some calculation mistake, one second now. Okay. So yeah, what have we done wrong here? Uh, should it be negative? That is the question. Mm, okay. T1 to T2 minus sign with it. Mm, yeah, I think there is some mistake with the signs because I'm getting negative answer. I'll check that. But since we are running out of time, we'll do some another problems. I'll correct this and I'll update in the notes later. But yeah, other than that, let's see. There are like different type of problems that you can think of. Hmm. Okay, I'll check that. This should not be like this, but let's see. So, maybe. Okay, I'll leave some space for it. So there is a question. So the spectral emissive power of this single emissive power E lambda for diffusively or diffusely emitting surface is, it is given as a function. So it is 0 for wavelengths less than 3 microns. It is 150 watt per meter square into micron when your lambda is in the range of 3 to 12, or maybe like this you can put. So when your lambda is in this range, it is 150, and then it is 300 watt per meter square into micron when your lambda is between 12 to 15 microns, and again it is 0 for lambda greater than 25 microns. Then total emissive power of the surface over entire spectrum is, and then this is like a data entry type of question, and you have to enter the value in watt per meter square. So since it's a diffuse surface, diffusely emitting surface, it is independent of direction. The emission is it is only function of your wavelength, and therefore the total E lambda, or you should not say E lambda because it is independent of lambda, then it will be summation of 0 to infinity E lambda into d lambda, or integration or summation, whatever, because here it is discrete, so you can write this way also, I equal to 0 to I tending to infinity, ei or e lambda I, that is for ith uh, wavelength, into d lambda I, or there is no need for d lambda here because it's like that only. Okay, so now here we know that these values are constant in this range, right? So basically what happens when, or maybe we'll follow one thing only here, it will be confusing to do it discretely again. So let's say it is a continuous like this. So then again, you know, this should be minus infinity to infinity, sorry. So minus infinity to 3 microns, you have 0 d lambda, plus maybe I'll drop microns because that is understood, all units are in microns. 3 to 12 it is 150 d lambda, 12 to 15 it is 300 d lambda, and 15 to infinity it is 0 d lambda. So these two derivatives are integrands are 0, so the value is 0. Here it is 150 is a constant, it will come out. D lambda integration is lambda, so that will be 12 minus 3 plus 300 again constant, 15 minus 12. So basically 150 into 9 plus 300 into 3. So the total will be 5250. Okay. Is it so? Oh, one second. It's not like that. So it's basically 900 plus 150 into 9 is 1350 plus 900. So 2250. So that is the answer. Okay, so these type of questions are there. Apart from that, yeah, then there will be like comparative questions. For example, the question is, if the temperature of a solid surface changes from 27 degrees Celsius to 627 degrees Celsius, then the emissive power will increase by how many times? So here again we know that emissive power is nothing but T power 4, assuming it is a black body. If it is not, then also it's fine, you know, or let's say into area will be also there because it's a power, right? It's not a flux. So sigma A T power 4. Sigma is constant, A is constant because the body is same. So emissive power is proportional to the T3 power 4. So therefore, E2 by E1 will be T2 by T1 power 4. And what will be T2? T2 will be 273 plus 627 divided by 273 plus 27 whole thing raised to 4. So this comes out to be 900 by 300. So basically 3 power 4. So that is 81 times. So your emissive power is increased 81 times when your temperature is going from 27 to 627. So this type of ratio questions are also there. Apart from that, Yeah, then there is like slight version of this is you know, like two spheres made up of same material have radii as, or let's say two spheres A and B, they have radii as 1 meter and 4 meter. They are maintained at 4000 Kelvin and 2000 Kelvin respectively. Then ratio of energy radiated by sphere A to sphere B is. So something like this is also asked. So in this case, what happens? Again, the governing equation is same only. It is a 4 power thing, right? So, but in this case, your power will be sigma into 4 pi R E square into T A power 4, right? So therefore, it will be E A by E B R A by R B square into T A by T B power 4. RA is 1, RB is 4. So this is 1 by 4 square, and TA is 4000 and TB is 2000 kelvins. So we need not to add 273 here. And power is to 4. So this is 1 by 16 into 2 power 4 is 16. So they are emitting same energy because one is having uh, larger radius while other one is having higher temperature, and their ratio is such that they are emitting in same ratio. Okay. So then let me see. We have 5 more minutes. Some sort of simple questions are there or not? Yeah. So yeah, this is sometimes they ask this in some interviews also. That how will you determine the surface temperature of sun? So there are various ways. One is using the radiation, because from sun the rays come to earth primarily due to uh, radiation mode of heat transfer. So it is mentioned that uh, the earth receives surface radiation from the sun at 1400 watt per meter square. The exact number is different, it is 1365, but let's say 1400. The distance from sun to earth is, it is surface to surface distance, 1.5 into 10 to the power 11 meters, and radius of sun is 7 into 10 to the power 8 meter. What is the approximate surface temperature of sun, assuming it has a black body. So the trick is same only. Here we know that emissive power is nothing but sigma A T to the power 4, right? So what they are expecting us to find out from here is now consider the sun as one second. Watt per meter square Kelvin, right? I think there is. The sigma watt per meter square Kelvin. This is watt, right? See, they have given watt per meter square, no? So, I mean, in the previous problem, here also, one second. Power is watt per meter square, but if you match the units, sigma is watt per meter square K power 4, so it becomes watt only, no? One second, I'll do the maths. Let's see. Yeah, anyway, we are at 8 o'clock. We should stop. So before, this is the last thing we'll do. So this is the calculator. 5 point. So 1400 divided by 5.67 into 10 to the power minus 8, and we need to take the fourth root of this. Okay. Yeah, I think some data is wrong here because one second. Yeah, so surface of the sun. This area is wrong, no? Because see, Radius of the sun is given, distance from the sun to earth is given. It should not be, I mean, I think there is something wrong in this question. Yeah. Yeah, because this calculation also doesn't make sense. But see, the total solid angle is 4 pi for a sphere. That doesn't also solve this. 1 second. Yeah, I think something is wrong with this question. This data is not correct. Typically, they use that Wien's law, etc. But yeah, it should be around 6000 Kelvin, the answer. But to have that 6000 Kelvin, so 6000 raised to power 4. This is quite a huge number. Yeah, so I think there is something wrong. This question is not entirely correct. Maybe I'll look into it later, but I think there is something missing here. So anyway, we are out of time also, and we'll take more problems in the next class also regarding the radiation and all. So for now, the only thing is this integration that I did, and somehow it is getting negative answer. So I'll sort it out, and maybe I'll add it to the notes.
Sir, what is the final answer for that one, sir?
This one. This one I also don't know the answer because I made up this question on the spot. Okay. I think it should be in some minutes, few minutes or something like that. Okay. Yeah.
Okay. So, thank you.
Yeah. See you next class. I'll figure this out and I'll let you know.
Hello, Hashir. ఏంటమ్మది కోర్స్ పైలా ఏం చేయలేదు కదా భయ అంతవరకే చేసింది అదే పెట్టినా ఓకే
Okay, then I'll stop the meeting for today. Let's meet next time.